So good morning all. In this section we will see the solution of wave equation. So we have already derived the wave equation in terms of magnetic and electric field as del square Es minus gamma square Es is equal to 0 and del square Hs minus gamma square Hs is equal to 0. Now the next step what we are going to do is we are going to find out the solution of this wave equation. For that you have to keep one point in mind, that is electric field and magnetic field are perpendicular to each other and both these fields are at right angles to the direction of propagation of B. So here what I have done is, for this derivation I have taken electric field along the x-axis and y is perpendicular to x, so I have taken magnetic field along the y-axis, and this x and y is perpendicular to z-axis, so I have taken the propagation of wave along z-axis. You can take according to your convenience, but the only difference is there will be change in the unit vector in your expression, that's all. Okay, so here I repeat, I am taking electric field along x direction, magnetic field along y, and wave propagation along z direction. Okay. So this is an important point. Electric field and magnetic field are perpendicular to each other and both fields are directed at right angles to the direction of propagation of B. Now I am writing Es as Esx of z into Ax. So this x represents the fact that electric field is along which axis? X-axis, and this z represents the fact that the wave is propagating along z-axis, and this Ax shows that the electric field is pointing towards the x-axis, so the unit vector is also along the x-axis. Okay, that's all. So now I am going to substitute this 2 in 1. So again write del square Esx of z minus gamma square Esx of z is equal to 0, and we know del is equal to dou by dou x plus dou by dou y plus dou by dou z. So I can write del Esx of z is equal to dou by dou x Esx of z plus dou by dou y Esx of z plus dou by dou z Esx of z. Then what I am going to do is I am going to substitute this del of Esx of z in equation A. So again write dou square dou x square of Esx of z plus dou square dou y square Esx of z plus dou square dou z square Esx of z minus this term, which one? Minus gamma square of Esx of z, that is written here, is equal to 0. Instead of del square Esx of z I have written this. Now here the first two terms will be equal to 0. Why? Because this is here the electric field is along the x-axis, here the electric field is along the y-axis. That is, this is the dou by dou x square term and this is the dou square by dou y square term, right? But you know this Esx of z is a function of which Ez? Esx of z is a function of Ez because the electromagnetic wave is propagating along the z axis. So this term will be a function of z. So dou square dou x square term and dou square dou y square term will be equal to 0. So only the z term will be remaining. So I can write dou square by dou z square of Esx z minus gamma square Esx of z is equal to 0. Now this is a scalar wave equation and is of the form of linear homogeneous differential equation. So this is a differential equation. So now what you have to do is, in order to find out the solution, you have to go to the solution of differential equation which you studied in your mathematics paper, which is not required here. So it's enough that you by heart this solution, that is Esx of z is equal to E naught into e raised to minus gamma z plus E naught dash into e raised to gamma z. So this one, so the solution of this is this. This is the solution Esx of z is equal to E naught e raised to minus gamma z plus E naught dash e raised to gamma z. Okay. So if the electric field is at infinity, what happens to the second term is it will become equal to 0 if the electric field is at infinity. Okay. So we will remove the second term from this solution. So I can write Esx of z is equal to E naught into e raised to minus gamma z. Okay. Now the next step what I am going to do is I am going to insert a new factor, that is a time factor e raised to j omega t. So I can slightly rewrite this solution as Esx z comma t into E naught into e raised to minus gamma z into e raised to j omega t. And you know what is gamma? Gamma is alpha plus j beta, which we studied earlier. So I can write E naught into e raised to minus alpha plus j beta z into e raised to j omega t. Then I am removing this brackets and rearranging. So finally I will get E naught into e raised to minus alpha z into e raised to j omega t minus beta z. From this expression we need only the real part. So I can rewrite it as E of z comma t is equal to real part of E naught into e raised to minus alpha z into e raised to j omega t minus beta z into ax. The unit vector is along ax because the electric field is pointing towards the x-axis, which can be written in another form as E of z comma t is equal to E naught into e raised to minus alpha z cos omega t minus beta z ax, which is a solution of your wave equation. And in terms of h, you can write the solution as h of z comma t is equal to h naught into e raised to minus alpha z cos of omega t minus beta z into a y. Here it is a y because the magnetic field is along which axis? Y axis. Now there is a relation connecting h and d, that is h is equal to E by eta, where eta is intrinsic impedance. Eta is intrinsic impedance. So I can write h naught is equal to E naught by eta, and eta is given by the formula square root of j omega plus sigma plus j omega epsilon, where sigma is a conductivity, which can be represented in the polar form as magnitude of eta into angle theta n or magnitude of eta into e raised to j theta n. These two are the one which I have underlined is a polar representation of your intrinsic impedance eta. Now next what I am going to do is I am going to substitute this phi a phi b in equation 4 or either in equation 3. Okay, here I have done an equation 4. So what I can do, h z naught z comma t is equal to, instead of this h naught I can substitute E naught by eta, and in place of eta I can substitute what? Eta into e raised to j theta n or eta into angle theta n or this one j omega square root of j omega plus this one. So here I have taken eta into e raised to j theta n. So finally the expression will look like this: h of z comma t is equal to E naught by eta e raised to j theta n into e raised to minus alpha z into cos omega t minus beta z ay. So if I am substituting, instead of eta e raised to j theta n, I can write eta angle theta n, right? So if I am substituting, instead of e raised to j theta, if I am substituting angle theta n, okay, that is this one. Simply this one, magnitude e raised to j theta n can be written as magnitude eta angle theta n, that is written here. So Now it will be like this: E naught angle eta, E naught by magnitude of eta into angle theta n into e raised to minus alpha z cos omega t minus beta z. The next step what I have done is I have taken this theta n to the numerator, so that I can write E naught by theta, so not eta is equal, sorry, it's not theta, it is eta. Intrinsic impedance is read as eta. So E naught by eta into e raised to minus alpha z cos omega t minus beta z, then this minus theta n into ay. So this theta n from the denominator is taken to the numerator, so that it becomes minus theta n into ay. It is another form of your solution for wave equation, and where alpha is attenuation constant and it measures the rate of decay of a wave, and the unit is Napier per meter or decibel per meter, and beta is a phase constant. It gives a measure of phase shift of a wave in a medium per unit length, and the unit for beta is radians per meter, and the relation connecting lambda and beta is 2 pi by lambda radian per meter. That's all, and this derivation is also important, so please write down and study. Next we will see a term loss tangent and loss angle of a medium. So you are familiar with the term current density of a medium, that is Jc, and displacement current density Jd. Okay, so you know the current density J is given by the formula the sigma E, and displacement current density is given by the formula J omega epsilon E. We studied in the Maxwell's equation. So here what I am going to do is I am taking the ratio of these two terms, that is JCS by JDS is equal to sigma ES by J omega epsilon ES. So if I am removing the modulus term, I can write it as sigma by omega epsilon. This J will be removed, then ES and ES will be cancelled. So finally I will get sigma by omega epsilon, which is the ratio of current density in a medium to the displacement current density. Now if I am drawing a graph with so current density along the x-axis and the displacement current density along the y-axis, and if I am drawing a line such that it makes an angle theta with the y-axis, then I can write tan theta is equal to, you notice, opposite by adjacent. So I can write what? Sigma ES by J omega epsilon ES, which will give you sigma plus omega epsilon. This is a magnitude. I am taking the magnitude, so I can remove J term, then ES and ES get cancelled, and finally I will get sigma by omega epsilon, where this tan theta is a loss tangent of the medium and theta is a loss angle of the medium. Okay, tan theta is equal to sigma by omega epsilon. So I can say that loss tangent determines how lossy a medium is. So the value of tan theta helps you to measure how much loss is there in a medium. So here you will see, now we will see two condition, that is if tan theta is very small, that is if sigma is much less than omega epsilon, then that medium is a good dielectric, or otherwise a perfect lossless medium. And if tan theta is very large, then that is if sigma is much greater than omega epsilon, we can say the medium is a good conductor. So I can say this tan theta determines how lossy a medium is. It measures a loss in a medium. Similarly, there is another representation for tan theta, that is tan theta is equal to epsilon double dash by epsilon dash, which is equal to sigma by omega epsilon, where epsilon dash is